Good afternoon. This is CIVE 634, and this is our class number 51 for 051, 5th week and first class of the semester. This is fall 2022. And the subject today is overland flow and then runoff. Okay, as I said earlier, before we started, we have to cover catchment properties, runoff, and then overland flow, because without catchment properties and runoff, we probably wouldn't get to very clearly to overland flow, which is a very complex subject. So what I'm going to do today is I'm going to cover the basic material, because I do realize some of you don't have the background. So I'm going to spend today covering what's in the syllabus already: catchment properties, and then runoff. And then Wednesday I'll get into overland flow, and then I'll just cover the whole everything else. I figure that can be done. So let's get started here. Catchment properties. Everybody can see the syllabus, right?
Yeah.
Okay, cool. So catchment properties. Catchment is a word that it's a bit confusing. The reason I decided to use the word catchment here, it's because this is my book. And when I wrote my book 33 years ago, it was 1989, I decided that I was going to classify from the start all the watersheds into small, medium, and large. And the reason for that being that I felt at the time, and I still feel, that these three categories lend themselves readily to treatment by three methods, which I had already: the rational method, the unit hydrograph, and the routing, which was reserved for the large catchments. Not reserved, but it was most applicable to the large catchments. So then the issue at the time, or my issue, was that the word catchment is not so much used in the US. It is used, but not as much as in England. We use in here the words watershed and basin, but there is no clear delineation of what a watershed is. Typically, a watershed is a small basin, and a basin is a large watershed. But what about something in the middle? So what I decided to do in my book is that I would classify catchments into small, medium-sized, and large, and then use the word watershed loosely to denote small catchments, and basin, large catchments. So catchment is the all-encompassing word for a part of the surface of the earth that collects runoff in one or at one point. So what kind of surface runoff then? How many types of surface runoff are there? Well, overland flow is the first one, the beginning of it. Then rill flow, gully flow, stream flow, and river flow. By the time we get into river, we're fine. We're in the large rivers. And as you know very well, the Amazon River is the largest river in the world, which has about 1/6 or 1/5 of the entire amount of discharge of all the basins in the world. So what is overland flow then? Overland flow, you can see it graphically in there. Overland flow, that's in the form of sheet flow over the land surface. Gully flow, we have already, no, I make a mistake. We've talked about gullies in our other class. I'm confusing here just because I showed that Camp Creek Gully over there. That's, I just got confused a little bit, but that's a typical example of gully flow. The third one becomes stream flow. This is a river. It could be anywhere. Actually, it's a river in Guyana. I had a job in Guyana many years ago, actually a couple of jobs that I had in Guyana. And then river flow, this happens to be the Columbia, near its mouth. Large river, as you can see. I believe it's the second or third largest river by way of volume in the United States. The sizes of the catchment, a catchment could be anything. My lot here, where I live here in North County, is actually a catchment because it has been graded by the builder when this house was built more than about 40 years ago. It was graded into into a catchment, to a small basin, so that I wouldn't be draining any water anywhere for legal reasons also. And because I live up on a hill up in Rancho Peñasquitos, that's the way they decided to do it. So my property is large. It's not too small or not too large either, but or not too big. But the point is that it's measured in a fraction of an acre. I think I have about 0.3 acres in my property, and this is already a watershed. The largest watershed, we have the Amazon Basin that has 6.915 million square kilometers and covers 8 countries in South America. So we say small catchments, small watersheds. In small catchments, we say the runoff is controlled by overland flow processes. So we're going to concentrate on overland flow now. Later on, Wednesday, we're going to talk about the math, the physics and the math of overland flow. Highly complex issue, by the way. Regardless of their size, catchments can drain either inwards into lakes or seasonally dry lakes, or outwards and head toward the ocean. So there's two types of catchments. The inland basins are referred to as endorrheic, and the peripheral basins, which are typically not inland, are referred to exorrheic, like getting out, exorrheic, like exit. So there should be no confusion. Here, there is a, I just put this thing this morning because I felt that I needed a better figure for the Great Basin. This is the Great Basin. As you can see, it covers, I read it this morning on the web, about 90% of Nevada, of the state of Nevada. I was thinking this morning that the state of Nevada, I don't know how it got its name. It must relate to snow in the Sierra Nevadas, which are out there. But in my mind, this state should be called maybe Salty State because it's full of salt. And the reason why it is full of salt is because it doesn't drain anywhere, so it collects. Why does salt collect in an endorrheic basin? Simple reason, because water is always falling in there, and water, just falling, run off the rivers, and the rivers contain salt, and the rivers head into the vegetation or from the vegetation, and the vegetation uses the water, and the more vegetation, the more salt is produced and runs into the rivers and eventually gets somewhere. It usually goes underground, or it goes into small valleys out there. If you note in here, look at this. This is the, I can't read it, Reso River or something. But you can see in here, there's a bunch of valleys over here. And I've overflown, a whole lot of them. I've overflown on Google Earth, and I invite you to do that too. If you want to fly over Google Earth, over the state of Nevada, and you'll see that it has a distinct white color. Not totally white, but like whitish. And why is that? Because of the salt accumulation. For how long? Well, millions of years. Okay, catchment area is the primordial, that is the most important catchment property, the area of the catchment. It determines the potential runoff volume, that is, provided the storm covers the whole area. Now, the catchment divide is the loci of points delimiting two adjacent catchments. That is the collection of high points, peaks, and saddles, separating catchments draining into different outlets. But however, there is subsurface flow. And oftentimes we have unusual things like this particular one over here, a river coming out of the ground in Peru. This is a large river, by the way. It just went underground and came out somewhere else. So if you started figuring out where this water, where did it come from? It came from underground. It's a spring, actually. It's technically a spring, or the river that goes underground and it comes out somewhere else. So it confuses the surface water hydrologist that is trying to determine the peaks and saddles so that he or she can come up with an estimate of the basin. I have an example here. Prior to GIS, maybe 20, 30 years ago, we were doing manually the area calculations. And I did this project. This one was in Campo Creek, in southeast San Diego County. And as you can see, I'm sorry, we went in there and determined the peaks from the topography, from the quad sheets, and the valleys, and then we were able to delineate the basin. That's the purple over here, and the rivers, and so on and so forth. The main river is this in red in here. I should mention at this point, though, that nowadays nobody's doing this because they're going to GIS and they're putting it together. I should also mention that GIS is not perfect, while this calculation is almost perfect. We had a chance many years ago, maybe 5, 6 years ago, to compare the calculation of GIS with a manual calculation from one of our basins, and there was an error of about, I would say, 8 to 10%, which I consider to be a little bit too much, but I am not going to criticize the GIS software because it is very convenient and very expedient. So maybe 10% error is not too bad if you consider that you did this work in 5 minutes or 15 minutes as opposed to 2-3 hours. Formulas for several formulas have been proposed to relate peak flow to catchment area. And this is an old formula, one of the first formulas. I believe this formula is about 150 years old. It was the first thing that occurred to engineers or hydrologists if they were going to base the discharge or the peak discharge. This was for floods. For the peak discharge, Q sub P, in the area, so they came up with a C and N, which are empirical coefficients. So this was really an empirical formula, and therefore it was not really rational. Now in 1889, there was a gentleman, I believe his name was Quitchling. I believe he was working in Europe somewhere, probably Ireland. I'm not sure of this though, but he came up with the rational method. He said the peak flow is equal to CIA, where C is the coefficient, is a runoff coefficient, I is the intensity, and A is the area. We will see later on that this method is called rational because, in fact, if you let enough time happen, the peak discharge of any basin will get to the value, the maximum value of intensity times area. So if you affect that with a coefficient, which is supposed to account for the infiltration, then you got your rational model in there. So obviously the rational model, which has been used for roughly about 130 years, is better than this equation 249. I said this equation would be the irrational equation. We don't want to use that word, but it is an empirical equation. Catchment shape. There are qualitative descriptors, or quantitative rather, descriptors provided by this formula and this other formula. This morning I worked this formula up and it came out nicely. It's been a while since I did this, so I decided to put it in the homework, in the assignment, for you to be Professor Ponce again and figure out how or where did this formula 251 originate, the compactness ratio. These are descriptors of the shape of the basin. Now, the typical shape of a basin resembles an ovoid, meaning like an egg, the shape of an egg. But many basins are not shaped like eggs. Okay, I had a chance when I was in Brazil many years ago to work with a basin that was like an eye. It was very skinny and yet it was very long. It was typically an eye, and it collected the mouth. The mouth was collected, or runoff was collected at the mouth, which was somewhere around the middle of it. So obviously, the more difficult or more different the shape of the basin is from an ovoid, it would be more difficult for us to figure out the runoff. We would have to do modeling if you wanted to do that. And it can be done. I mean, modeling is now, with the help of HMS, can be done readily by many people because you're not developing the model, you're using the model. Now, as the issue of using and developing models, I don't know if I talked to you about this, but my guess would be that 99.5% of hydrologists or engineers out there are using the model. They're not developing a model. To develop a model, you require expertise. You typically require that you get an advanced degree. definitely a master's, if not a doctorate degree, in order to develop a model. Not too many models are used out there. A few models are being used. Yet, if you want to study deeply the subject, you would have to become a developer of a model. As we have over the last 40 years, we've developed a few, I would say, handful, maybe 5 or 10 models. And I'm going to show you one of them on Wednesday. We have a meeting on our class on Wednesday. I'm going to show you one of them. This one, for instance, is a project, or rather, it is a hydrograph. It's the hydrologic response of La Leche River Basin. This was a project that we had in the year 2008 in northern Peru. We were charged with developing the emergency spillway hydrograph at the dam site of La Calzada. So we developed this. This is an unusual hydrograph because the basin was unusual. It was a large basin. It was about 1,000 square kilometers. Half of it was arid and the other half was humid. So the question is, when it rains, how does it rain? And if and when it rains, how does it run off? Given that there are differences between the arid rain and the humid rainfall. So we worked very hard. We worked for about a year on this project. And we finally were able to come up with the emergency spillway hydrograph at La Calzada. There's an emergency spillway hydrograph, and then there's a freeboard hydrograph, which is a little larger. Actually, if I remember correctly, the freeboard hydrograph had about the same shape, but it came up to about 6,000, a little higher. Because there's differences between the emergency spillway hydrograph and the freeboard hydrograph. The freeboard hydrograph is going to take the entire space between the design flow at the spillway and the crest of the dam. Relief. Relief is the elevation between two reference points. Maximum catchment relief is the elevation difference between the highest point in the catchment and the catchment outlet. The principal watercourse is the central and largest watercourse of the catchment and the one conveying the runoff to the outlet. So what I'm going to do right now is I'm going to stop this and I'm going to go back and show you a video that we produced recently. It's a kind of a fun video. I hope you enjoy it. The issue is, what is the source of a river? Where did it originate? It originates before you have a stream, when you have overland flow.
The source of a large river system, for example, the Missouri-Mississippi River, the largest in the United States, is often taken as a location of the uppermost spring in the farthest tributary. Under this optic, the source of the Missouri River would be Brower Spring, located in the headwaters of Hale Roaring Creek in southwestern Montana, near the border with Idaho. The spring is named after Jacob V. Brower, who in 1896 declared it to be the source of the Missouri River in his book, The Missouri River and Its Outmost Source. However, the name Brower Spring is not listed as an official name on the Geographic Names Information System maintained by the U.S. Geological Survey. The Missouri River is the longest river in North America. With its source in the Rocky Mountains of western Montana, the Missouri flows first north, then east and south for 3,767 kilometers, that is 2,341 miles, before joining the Mississippi River north of St. Louis, Missouri. The river drains a sparsely populated semi-arid watershed of 1,370,000 square kilometers, that is 529,200 square miles, which comprises parts of 10 U.S. states and 2 Canadian provinces. Although nominally considered a tributary of the Mississippi, the Missouri River is much longer and carries a comparable volume of water. The combined Missouri-Mississippi forms the world's 4th longest river system in the world. The longest tributary of the Missouri River begins a short distance upstream of Brower Spring in southwest Montana, on the southeastern slopes of Mount Jefferson in the
The Continental
High
Divide,
mountains of the Bitterroot Range. From there, it flows.
I can't get this thing. The Continental Divide is on the border between Idaho and Montana, I believe.
First as Hell Roaring Creek, then west into Red Rock Creek, then it swings northeast to become the Beaverhead River, and finally it joins with Big Hole to form the Jefferson River. The latter joins the Madison to become the Missouri River at the Missouri Headwaters State Park near Three Forks, Montana. The true source of the Missouri River is in the Rocky Mountains on the U.S. Continental Divide at 44 degrees, 33 minutes, 27.2 seconds.
Right, the water falling over here, it's going to one state, and this is for another state. This is the Continental Divide.
North, and 111 degrees, 28 minutes, 9.55 seconds west, at an elevation of 2,864 meters, that is 9,396 feet. By comparison, Brower Spring is at 44 degrees, 33 minutes, 0.7.
So there's going to be overland flow in here and infiltration, and that is going to be coming out at Brower Spring over here.
24 seconds north, and 111 degrees, 28 minutes, 25.2 seconds west, at an elevation of 2,684 meters, that is 8,806 feet. This table shows the geographical data for the 2 points. The geodistance between the 2 points may be calculated using the online calculator Online Geodistance 2. The result shows that the geodistance between the 2 points is 886.64 meters, that is 2,908.9 feet. The Lewis and Clark expedition, which lasted from May 1804 to September 1806, was the first official American expedition.
So I'm going to stop it there. You can continue on your own later on. I'm still over here. Overall relief of a catchment described by hypsometric analysis. I'm going to skip this part because it's not too important for our purpose, but I urge you to read it later on. The important thing about this section in here is that we are going to have typical rivers are like this, exponential. Always, the slopes are always decreasing. That's a typical river. But there are rivers that are not typical, like this one. This one's controlled by the geology, by uplift. There's one point of uplift here, another here, and a third one over here. Yeah, I'm not sure I showed this graph to you guys. I think I've showed it to the other class. My memory, I've shown it this semester, but this is a typical graph that I always use to show uplift and tectonism. But as you can see, that's not typical, and so we need to keep in mind that that is the case. That may be the case. In certain unusual geomorphological settings, inland rivers may feature very small channel gradients. For instance, the upper Paraguay River near Puerto Murtinho, which has an average channel slope of 2 centimeters per kilometer. This is about as low as it does get. Although in our book we have documented values a third of that, but those were in connection with large tidal rivers. That is, rivers that are next to the ocean. And since the ocean is a very huge, imposes a very huge boundary condition, then that is not really a river. It's already an estuary. Okay, so calculation of slopes, there are several formulas. The first formula is the S1, then the S2, and the S3 even. There's a third formula for the calculation of average slope. Not going to dwell on that other than to say that S1 is the easiest to calculate, but S2 may be the more physically accurate in terms of being representative of the entire channel. And calculations of these types of these three slopes can be made. We also have a calculation based on Manning equation, in which the time of travel is assumed to be inversely proportional to the square root of the slope. So we figure this equation here by considering the summation of all the lengths, and this is the summation of the individual lengths. This is the summation of the individual lengths divided by the slope, which has a way of figuring out of determining what's going to be the time of movement, and therefore we get this equation. It's a bit confusing, but it can be done. We can think about this equation. Another equation is the Ses Grid Method, which, by the way, it's easy to do now, presumably, if you have GIS. Prior to GIS, 30 years ago, we've been doing this calculation for 40 years. The GIS only came about in the mid-90s, I believe. Yeah, by 20 years, maybe 30, 25 years for GIS. And prior to that, it used to be done by hand. It took a lot of time to do this sort of thing. But we got it done. We got it done. And there's an example in here of the calculations S1 and S2 and S3 that I urge you to review. Linear measures. Why do we need linear measures? Well, watersheds are not oval or ovoid shape, not all of them. So therefore, we need to develop an issue of linear measure because we are looking at response of the watershed to rainfall, and the response is a function of the linear measures. So the standard linear measure are two: the catchment, catchment hydraulic length, which is L over here, the total length from the upstream point, very close to the border, or rather to the headwater. We call this the headwater. Very close to the headwater all the way to the mouth, that's the catchment hydraulic length. The other linear measure that is much used in unit hydrograph theory is the L sub C, which is the length from the mouth to the centroid. And the centroid is the center of gravity of the basin, which must be determined in some reasonable way. Topology. What is topology? It's a fancy word. It means regional anatomy. Example, our body. There's a certain topology to our bodies. We can eat with our hands. We don't eat with our feet, right, or with our legs, because that's just the way we're put together, right? Likewise, for the rivers, you can't have water jumping from one place to another. It's got to proceed in an orderly fashion. And for that reason, we have to discuss the issue of topology. What is the topology of the stream network? In other words, how many orders and how many first order, second order, third order streams? So we define what is stream order. The concept of stream order classifies streams in a network following a hierarchical numbering system. Overland flow can be considered as a hypothetical stream of zero order, because we're often asked to calculate overland flow, and we have overland flow models, but typically that would be for a small basin. If we have to have a large basin and we still want to use overland flow, then we can use a system like HMS that will put together the watershed in terms of the order of the sub-watersheds, so that can be calculated through the use of a model. Here I have two examples of stream order. As I say in there, two first order streams combine to form a second order stream. For instance, over here, first order stream, first order stream, second order stream, two second order streams combine to form a third order stream, and then two third order streams combine to form a fourth order stream. I believe it's been published in the literature that the Mississippi River is a 16, or rather 14 order stream. But I do not believe anybody out there has done an entire calculation for the Mississippi, because it's too big a project. I really honestly don't believe that there is such a thing. Just as much as there's no complete model of the Amazon Basin. It occupies or encompasses 8 countries in South America. But if you have smaller basins, yes, that can be done. I've done several projects with smaller basins and within one country. If a basin encompasses or spans two countries, that is a problem. We did the Santa Cruz River in Arizona back in the year, I believe it was the year 85. And 13% of that basin is in Mexico. And we actually couldn't go out there. So we had to kind of hand wave a little bit because we could not go out there to get the data for the 13% of the basin. But we figured that 87% was good enough, and we came up with what we considered to be good results at the time of the modeling. We did extensive modeling of the Santa Cruz Basin in Arizona. Where is the Santa Cruz Basin? It's the river that goes through Tucson, but it goes into Mexico. Like I said, 13%, because it's in the southern United States, abuts with Mexico. The Fastetter coding system. First of all, who is Mr. Fastetter? Or Dr. Fastetter? I'm not quite sure. He is a gentleman that originates in Brazil. Although I'm not sure, because Brazil has a lot of immigration. And Fastetter, I believe, was originally Austrian. He may have been a young man when he moved to Brazil for good. He settled in Brazil. And I happen to know Fastetter. I actually did a project back in the year 79 over there and had to deal with him. I met with Otto. His name is Otto Fastetter. The name Otto already depicts that his origin, which is from Austria. So he was out there, and in the mid-90s, or 80s rather, he had to do a lot with classify a lot of rivers and so forth, and he came up with this coding system, which is referred to as the Fastetter coding system. Widely accepted methodology for the description of watershed basin topology. Widely accepted means global. He was lucky that he was at the right place at the right time. I don't know how that happened, but USGS started using his methodology, and right after that, everybody in the world started using the Fastetter methodology. Most people don't even know the origin of Mr. Fastetter, by the way, but it was a good one. It was a good one. Albeit it was kind of simplistic, but it had to be done because there's a lot of complexity associated with the topology of river basins. So what did Fastetter do? He classified, let's take a look at the map because I think it's going to be easier for us to look at the map. For instance, in here, we have on this basin over here, and this is an example that I pull out of the web, by the way. So what he did was that he took the river and divided into 9 sections or 9 watersheds. The odd watersheds and the even watersheds. The even watersheds were going to be watersheds proper, like this one, 82. This is a mouth of the 82 watershed. Okay, 84 on the other side. This is technically the way he wanted it to do. He wanted to do it. 84 is also a watershed in the green in here. 86 is also a watershed, and 88 is over here. Then the intervening reaches of the river also are watersheds. They are kind of lateral watersheds. So he called them the odd watersheds, 81, 83, 85, and 87. And the headwater watershed, that was the 89. And by doing this simple division, he was able to come up with a general classification or general topological description of any watershed. It became very general. So that's a good part of Fastetter's methodology. Look at here, the 84, which is this gray area over here, it's this area. So then he was able to call it 84.1, 84.2, 84.3, 84.4, 84.5, 84.6, 84.7, 84.8. And this is kind of a little bit confusing in here, then 8.49. So you can see that's the way he, and there were typically sometimes in nature, there are endorheic watersheds within a larger watershed. So he decided to call that a zero watershed. And in this graph, it is shown as red. So you can see the 80 watershed is shown as red. So summarizing, The basin type have no inflow, and yes, they have outflow. So those would be over here, like this one over here. They have no inflow over here, but they have outflow. Then the inner basin watershed, they have inflow and they have outflow. And the internal basin, they have inflow, but they have no outflow. And the inflow over here is from precipitation. So with this, then he was able to do that. And like I said, he became famous. He passed away, I don't know, maybe 20 years ago. He was already kind of old when I met him in 1980, 79. Great guy. Actually, I looked at a project that he had designed, which had failed at the time. That's a story, which is a hydraulic story. I'll tell it some other time. Drainage density. Drainage density is the ratio of total stream length to catchment area. And why is it important? Because the more the density of drainage, the faster the response. And we're interested in analyzing the response. That means how fast does it take, or how fast is the response, meaning the hydrograph that is coming at the out at the mouth of the basin. And that is very important. That's why drainage density is important. There's a formula for the mean overland flow length. Oftentimes we have to look at mean overland flow lengths, and this is the formula for the mean overland flow length. Drainage patterns. We have various types of drainage patterns. I pulled this out of the web some report. Dendritic, which is a standard, typical one, rectangular, and these patterns, these rectangular patterns or drainage patterns would depend on the geology, on the underlying geology. Radial, coming out of a mountain, trellis, where there's fractures, and there's typically fractures out there. We don't know the geology. We need to, in order to know hydrology well, we need to have a knowledge of geomorphology and the associated geology too. And over the years, we have developed that expertise, but this is an expertise that is not very common to engineers. So either you learn it through practice, or you hire a specialist that would help you out with the project. Typically, that's what's done now. More and more, we have the specialists that will decide things on a very minute basis. This is another figure on drainage patterns that I pulled out from a photogrammetry journal a long time ago. Like this was 40 years ago. The dendritic is the more common one. That's the number one. But then we have radial, and this is just a black and white kind of repetition, a little more comprehensive than that other color figure that I showed you. Thermokarst. What is thermokarst? Thermokarst refers to the situation where the geology, the local geology, is karstic, meaning geology porous and has a lot of water in there, and therefore it's very hard to get runoff on the surface. The runoff is typically underground. Well, a case in point is the peninsula of Quintana Roo in Mexico, where Cancun is. If you visit Cancun, try to look for the rivers out there when you go out there. If you visit not just Cancun, but if you go out there and try to visit around maybe the pyramids and stuff, I tell you, you will not find any rivers. I tried and I couldn't. And I wonder why was that. At the time I didn't know. This was 30 years ago. It turns out that all the rivers in that area are underground. That's why there are no surface rivers. Why? Because of the karstic geology. Okay, we'll move on to the next subject right after describing the catchment and its properties. Now we move into the subject of runoff. Surface runoff refers to all the water flowing on the surface of the earth, either by overland flow or by channel flow in rills, gullies, streams, or rivers. Continuous process by which water is constantly flowing from higher to lower elevation by the action of gravitational forces. Now, how do we express runoff? We express it in terms of volume, runoff volume, or in cubic feet, cubic meters, or flow rate, cubic feet per second, cubic meters per second. In hydrology, we also express runoff in terms of depth by dividing the discharge over the discharge over the area, the total volume over the area becomes depth. You can say a runoff of 1 inch. Yes, that means that you took the volume, the total volume coming out or being derived from the integration of the hydrograph, and divide that by the area, and then you get the runoff. So there's various ways of, or units that we could use to describe runoff. Runoff is typically CFS or inches, or also you can express runoff in peak flow per unit of drainage area in some methods, or peak flow per unit of runoff depth also in some other methods, or peak flow per unit of drainage area per unit runoff depth, like in the TR55 method, which we're not going to cover in this class, but that's a method that has become popular over the last 20, 30 years, because some people argue or that it improves on the rational method because it has more information. That's another story, but there are various methods out there for various different calculations have various methods. Runoff can consist of 3 sources: surface runoff, inner flow, and groundwater flow. And here's the confusion, by the way, or there could be some confusion. If you see a river, look at the river, look at the water flowing in the river. Well, could that be called surface runoff or not? And the answer, most people say, oh yeah, that's a surface runoff on the river. But some of it could have come from the base flow, that means from the groundwater. And that's technically not runoff that ran on the surface first. Now it's running on the surface, but it was after filtering through the underground passages. So there is a confusion, which has led to confusion in the issue of the definition of the runoff curve number, by the way. The runoff curve number should have been surface runoff curve number, but because a long story that I precisely or particularly have asked you to answer that question as part of the homework, is that there's some confusion in practice as to what exactly is surface runoff. Surface runoff theoretically is the runoff that goes on the surface before joining the channels. Once it joins the channels, then it becomes river runoff, I guess you could say, which may or may not have groundwater flow, that is base flow. This is a good graph. This is a graph from USGS, I believe. I don't know. I don't see the credit over there, but it is a USGS graph. Flow of groundwater, the water table, capillary fringe. Those little arrows denote or represent the capillary fringe, and then the so-called vadose zone and the zone of saturation and the vegetation on top. How deep is the vadose zone? It depends. I think when Mainzer did his study, 1927 study of groundwater in the entire western United States, because he was working with the GS, Geological Survey, and they commissioned him to do a study of how deep was the groundwater in the western United States, with the intent of exploiting it or pumping it out. Why? Because in the eastern United States, it was not a problem. The groundwater was right there within 2 or 3 feet, and everybody knew it because it's a humid area. But in the western United States, it was a dry area, arid area, and we really didn't know or could not guess how deep was the groundwater. So the GS commissioned Mainzer to do the study, and he came up with a tremendous, very great study in 1927. He basically almost single-handedly created the subject of ecohydrology, because he said that in no uncertain terms, the depth of the groundwater depended on the type and extent of vegetation on the surface. Fascinating. What does groundwater have to do with vegetation? Well, that's exactly the point that he was making, because the vegetation is going to look for the groundwater in order to get the water when it's not raining. And in arid areas, it typically doesn't rain enough. So the vegetation has to look for the groundwater. So you can see, therefore, according to Mainzer, and he's correct, that only in the places where the groundwater is within reach of the vegetation, and it'll depend on the types of vegetation. Some vegetation will send their roots to 10 feet, others to 20, 30, all the way up to 50 feet. There are some trees in the United States, in the western United States, like the mesquite, that are known to send their roots to 50 or 60 feet of depth in search for the groundwater. That is, in search for the vadose zone, not the groundwater. Because once they get to the vadose zone, they're able to survive by pumping the water from the vadose zone. That's the vadose zone. This is a very good graph that I like. It's a general election of groundwater flow. That's the way it works. Groundwater is always moving, always moving. There's always a gradient. If groundwater doesn't move, it gets stuck. And if it gets stuck, it surfaces. And if it surfaces, it evaporates. So it's gone. So the fact that groundwater is always moving contradicts this, because it's always moving, and it's always moving toward lower elevations by the action of gravity. So this is a not the scale. That is, the vertical scale has been exaggerated in order to show the depressions where the rivers function. And rivers, when they are humid area rivers, they carry water all the time. So if it is not raining, then the water is coming from the groundwater as base flow. We know that to be the case. It occurs to me that about 250 years ago, there was a scientist in France, I believe in the 1770, so that would be 250 years ago, right? Exactly. And one day he came up with a big idea. He said, "Now, fellas, I know where the water in the rivers is when it's not raining." He said it was coming from the ground. Can you imagine that idea, that the groundwater is feeding the rivers in the wet areas? It's only 250 years old, roughly 250 years old, but it is coming from the groundwater. The difference, of course, between surface water, meaning the water that runs on the surface, and the groundwater is that both of them are diffusing, but they're subject to different diffusion equations. The diffusion of the groundwater is very strong. So most of the peak is gone, and it all comes out as very mild flow. While the diffusion of the surface water is very weak, sometimes it doesn't even exist. When the diffusion of the surface water does not exist, we give it a name kinematic flow. If it diffuses a little bit, we give it the name diffusive or diffusion flow. And it diffuses a whole lot, which is unusual, by the way, then we give it the name dynamic flow on the surface, as you can see. So diffusion plays an important role both in the groundwater as well as in the surface water. Streams may be grouped into three types: perennial, ephemeral, and intermittent. I believe I do have pictures over here. We have perennial stream, Indian Creek in California. I took this picture back in the year '89. I had a project in Northern California. What was the name of that county? Plumas County, right. Plumas County, in Northern California. It's about 5-6 hours northeast of San Francisco. I don't know if you guys been there, but it's a nice part of the state. So as that picture shows, this is a perennial creek or stream. It's called Indian Creek. This one, on the other hand, on the right side, that's an ephemeral stream. I took this picture. This is the Mojave River. One day I was out there. I'm not sure exactly what I was doing, but I ran into the Mojave River in Helendale. This is in Helendale, central eastern California. If you can see, there's hardly any, and there's no water out there. It's an ephemeral river. It only runs when there's a lot of rain. This one, it's an intermittent stream. This is Rosarito Creek, and also the Gila River in Arizona is also considered to be intermittent. Look at this river. It also has the flood over here. It's dry, as you can see, but when it floods, and this river has a way of flooding because it covers almost the entire state of Arizona. When it rains, it could rain a lot. I was there in the year 1985. We had a project over there to calculate the hydrology of the Santa Cruz Basin. And the Santa Cruz River ends at the Gila. and then it moves through northwestern Arizona and gets all the way to California, where it drops its water into the Colorado, next to somewhere out there. I don't remember the name right now. Surface runoffs and base flow. So surface runoff should not be confused, or at least one should specify what kind of surface runoff we're talking about. Is it the total surface runoff combined with base flow, or is it just without base flow? That we need to specify, or at least make it clear in our projects which one we're talking about, because I do repeat, there is some confusion in the literature. Antecedent moisture. It's a concept that was around, has been around, but it was developed and used very much by the Soil Conservation Service, because they, at the end of their MACA's efforts back in the middle 50s, they decided to classify the knobs that they were going to put into their model into 4: soil treatment, surface treatment, and the third one was the grazing condition, pours, fair, etc. And the fourth one, they could not agree as to what to call the fourth, because they had 4, 5th, 6th, and 7th. So they decided to call it AMC and consider it to be a surrogate for any other, or all the other types of influences on the runoff. That truth was revealed to me by none other than Don Woodward when I met with him in the year 1996 in DC. I didn't know at the time because it hadn't been published, but he confided it to me, and then I published subsequently. I thought that was important to realize that what had been done, because otherwise people like myself and others were asking, okay, you guys have 4 variables. Where about the others? Where are they? Where's the variation in time, variation in space, all kinds of other stuff was there. It was not important, not as important as the first 4, but they were important enough to perhaps be discussed or even considered. But no, then Don said no. The antecedent moisture was supposed to take care of all the variability. So I have an example in here of a catchment with high antecedent moisture, definitely. This is Campo Creek. We did a lot of work in Campo Creek in the years 2000, 2001, 2003, all the way up to 2005. We actually did the hydrology of Campo Creek around that time. Rainfall runoff relations. There's an equation here, 257, which is the precursor of the curve number method. And why did I put it in here? Because I felt that for historical purpose, it was necessary to present first the original idea. That was the original idea, but it didn't work too well because it went like this. Subsequently, Marcus came and said, no, that's not the curve. It should not be a straight line. It should be a curve. And I'm going to figure out what shape should the curve have. And then he invented that famous equation that I have discussed last week with you, that I went over there and visited with him, and one of the intentions was to ask him, where did he get that equation? And he said that was the best equation that fitted his data, the data that he had, which is several Midwestern United States had developed over the course of 20 years the data for the development of the equation. And that's what he did. We do believe now that the Marcus method, if it's not correct, it's very popular and has already been used a lot. It's like Manning equation. Like Manning equation is not correct. Of course it's not correct, but it is very popular. If I stood out there at a conference and started talking bad about the Manning equation, I would be clobbered by the engineers. They've used it for 100 years. They're going to say, who's this guy that's telling us that the Manning equation doesn't work? Same thing in here. We've used this equation for a long time. What we need to do is improve it, because I already told you last week, no other method has proven its superiority compared to the CN method. Even our friend Roger Smith, well, he's not my friend, but he's an acquaintance or a colleague, he also agreed to that in his discussion to our paper with Hawkins that was covered last week. Runoff concentration. This is a very important concept in what we're going to be discussing. And that is, I want you to read this carefully. It says the concentration property. Assume that a storm falling on a given catchment produces a uniform effective rainfall intensity. First, the rainfall intensity has to be effective, meaning discounting infiltration, and it has to be uniform throughout the area, distributed over the entire catchment. Surface runoff will eventually concentrate at the catchment outlet, provided the effective rainfall duration is sufficiently long. What is going to be the discharge? Q sub E, equilibrium flow rate. There's going to be an equilibrium flow rate, and it's going to be equal to the intensity, effective intensity, constant, times the area. That is the formula. That is a conceptual formula, and I would say also a deterministic formula. There is no other formula to describe this. There's only one, and there will always be one. So it's got to be physical. I times A. And that's the basis of the so-called rational method. The only difference between this formula and the rational method is that instead of putting I sub E in here, the rational method has CI, where CI is equal to I sub E. That's all. So that becomes then a rational method. There's three distinct types of catchment response. This subject is in my book, I believe, only in my book. Because when I wrote this book, I considered myself an expert in routing and in watershed routing in particular. So I thought that this was correct and it needed to be put out. But I reviewed a lot of books and none of them had it. So I decided to put it in. What's going on here? The concentrated catchment flow, which gave its basis to the rational method. This is the graph that depicts the functioning of the rational method. Constant rainfall intensity, effective rainfall intensity, a certain duration, and when that duration of the rainfall is equal to the time of concentration, it reaches a peak. And when it stops, it starts dropping, receding. It is not a triangle, an isosceles triangle, but it is more or less a triangle. It goes up and it goes down. It may not be perfectly, it will not have the perfect shape of a triangle, but that is the idea. That's the formula. What happens now when we have a rainfall that exceeds the time of concentration? At that point, all the rainfall will be contributing, from the entire watershed, and therefore this would not grow above the maximum peak. It will just stay constant like this until the runoff, until the rainfall finishes, at which point it'll start receding. So that's what we call super concentrated catchment flow. Not a whole lot of applications. Why not a whole lot of applications? Because what we're interested is in the peak flow. And with this, we get the same peak flow. So there's really not a whole lot of applications. This is for theory, for describing the problem. But this one over here has a lot of applications. Because what happens if the rainfall doesn't last the time of concentration? The time of concentration is larger than the rainfall. Then it would not reach its peak and it start coming down. Does this happen in nature? And the answer is yes. The entire theory of mid-sized catchment analysis is based on sub-concentrated catchment flow. When Sherman, that all but invented the unit hydrograph in the year 1932, I said all but invented because some people have argued that he didn't. But anyway, he ran with the credit. Sherman invented the unit hydrograph. That's what most people say. He was a big hydrologic engineer of the times. These were the times where many dams were being built in the United States, and I am sure Sherman participated in a lot of projects as the hydrologist of record. And he had to come up with some formula to design the spillways. And he tried the rational method at the time. By that time, the rational method was about 40 years old, from 1890 to about 1930. But he found out that the rational method was always over dimensioning or over calculating the discharge. And he figured there must be something in here that I'm not considering. So he thought about it for a long time. I don't know how long, but I'm talking years in here. And he figured out that the larger, the mid-sized watersheds that he was dealing with were actually sub-concentrated. That the rainfall, the time of concentration, well, they were sub-concentrated in the sense that T sub R was greater than T sub C, and therefore they could not achieve any more than just a limit on the flow in here. And he developed the concept based on that. He developed the concept of the unit hydrograph, because the unit hydrograph is a way of accounting implicitly for the diffusion in the watershed. Now, diffusion is an interesting word because a lot of people don't know what it means. Okay, diffusion means to obliterate, to kill, to attenuate. And how do we use it? We use it, I've used the word diffusion for 40, 45 years. Some people call me Dr. Diffusion, by the way, because we used it so much and we wrote so many papers on the concept of watershed and channel diffusion. So because of diffusion, according to Sherman, I'm forgetting here the names now, these concepts could be pursued. So we have the sub-concentrated catchment flow over here. We also have a calculation in here of what I just said, sub-concentrated, concentrated, and super-concentrated flow. You can see in here that the sub-concentrated flow never reached the peak. The peak is over here. It never reached the peak and it was cut. So it had to become sub-concentrated. The concentrated reached the peak. It was just able to reach the peak. And the super-concentrated reached the peak earlier. So this was super-concentrated. Now, how did we develop these hydrographs? These hydrographs over here, they are simulations, idealizations. But over here, these are calculated hydrographs. We calculated these hydrographs with a model that we call Overland, and I will discuss that, the operation of that model, as the last thing I'm going to do this week with you guys. The Overland flow model allowed us to do these calculations and show exactly what was going on. I should mention to you at this time that we were the first ones to do this in 1986, and then subsequently later on in 1997 with this model. This paper, I believe, is the year 2000. In the year 2000, I had a student, and I was looking at this, and I asked her to run all kinds of runs with different conditions, different areas, different intensities, and so forth, because I was interested in plotting this graph for various cases, and we were successful in doing that. And one thing about this model that we used, that we developed, is that it is grid independent. What does grid independence mean? I know that those of you that took computational hydraulics last year have heard me talk about grid independence. Grid independence refers to the property of a model not to change in results if you change the grid. That means grid independence. Many models do that, which means that they are not completely controlled by the numerics. Time of concentration, a very complex actually, but simple subject because it has been made into formulas. And there are some formulas out there. Some of them are, there's one that is better than the others, and I'll point to you which one of them. But the time of concentration is the time that it'll take in a parcel of water to move from the farthermost part of the watershed to the mouth. And it is used in urban drainage design. So we need to calculate, always in hydrology, we need to calculate the time of concentration. Unfortunately, there's various formulas and they all differ. To my knowledge, there is no coincidence between the various formulas for time of concentration. Why is that? Because the formulas are different. The more popular formula is called the Kirpich formula, but it is the less accurate because it only contains L and S as parameters, and the rest, the other two parameters, three actually, the other three parameters are bundled into the coefficient, which means that this formula is not very accurate. And yet everybody uses it. Most of the Autodesk formulas or software out there that everybody uses for design are using the Kirpich formula. Next to the Kirpich is the Kirby-Hathaway formula, which includes another term in there, the friction, but again, still misses something, and therefore it has to have a 0.6. Note that this first one is 0.06, while this one is 0.6. So the introduction of the n into this formula already made the coefficient multiply by 10. How fascinating. Okay, n is a roughness parameter. That means that the Kirby-Hathaway formula has a roughness parameter, while the Kirpich does not. What are we talking about this roughness parameter? It's an n. It looks like a Manning's n. Well, it is a Manning's n, but not for turbulent flow. It is for laminar flow, and that's why it is much higher. Laminar flow is slower, and therefore there's more friction, and therefore the n has to be higher. So note that if you're looking at these that are extremely high, they're almost 10 times more than the normal condition for channels. The normal condition for channel will be 0.00002 actually. And in here you have, no, I'm sorry. I take that back. This one's correct. But look at this. It jumps immediately. It jumps to 10, 20, 40, 60. It gets all the way to 0.8. 0.8 is very large to use. And yet, this table is part of the manuals of practice of the U.S., both SCS as well as the Army Corps of Engineers. So they have to be correct. Now, case in point. Back in the year 2007, I believe, I was in Florida at a project, and there was a panel. There was 6 people actually, 6 experts, professors throughout the United States, and one from Canada, had been invited to review a model that South Florida Water Management District had developed. And they were at the time on the Everglades considering a Manning's of 1.0. 1.0. And I at the time queried them, and I said, they're higher. I said, because in my book, and this is my book, you're looking at my book right now. In my book, I follow practice of U.S. Army Corps of Engineers, and they said that the highest condition or the largest number for Manning's N under laminar flow, not laminar flow, laminar flow, but for overland flow was 0.8. And they went back to the drawing board, and the next day they came back and they said, we're standing by our number. We believe that in the Everglades, the Manning that we're going to use, the N value that we're going to use, the frictional value for laminar flow conditions should be 1. So they're beyond what I wrote in my book. I never actually considered changing this table because this is a table that was developed by the Army Corps of Engineers based on many, many projects. The Florida project and the Everglades, I believe there's only one Everglades or similar type wetland as large and as wetland like the Everglades in the United States. So I didn't think it was necessary that I should change the formula. Over here, the Papadakis Kazan. Papadakis was a friend. He passed away maybe 10 years ago. Papadakis was a professor over at Colorado State University, and he got together with Kazan, who appeared to be one of his students, and they applied for a couple of years statistics on all the data. They had a lot of data, and they came up with this equation. Now, notice that the Papadakis Kazan is a little different than the Kirby-Hathaway because it has an I in it, in the denominator, which is the way it should be. They still have a 0.66 in the front because there's one more piece of information in there that Papadakis Kazan did not put in there, presumably because they couldn't do it. I do realize that these things are difficult from a statistical standpoint. And finally, we have a physically based approach to the calculation of time and concentration by overland flow. It's a first approximation. Time and concentration can be taken as the time to equilibrium of kinematic overland flow. Remember, I already talked about kinematic, diffusion, and dynamic. And note now that if you compare the kinematic overland flow, these formulas look pretty much the same, don't they? Look pretty much the same, but this one has an M. And M is the exponent of the unit width discharge flow depth area rating. So typically for a Manning condition, the M would be 5/3. Yes, 5/3, that's the standard. So if you put 5/3 in there, then it's kind of the same as over here. 5/3 is 3/5, 3/5 is 0.6. So this would be 0.6 for 5/3, while this is 0.52. That's not too far, all things considered. So we believe that, that this equation may be the best. However, there's a caveat in here. It's the best from a theoretical standpoint, but we have considered that the plane is straight and rectangular. And very few watersheds out there are rectangular in shape. So there's a drawback. In other words, theoretically, if you could consider the planes to be rectangular, this would be the best formula. But it isn't, because we don't find any rectangular planes, very few out there. So I would say that at this point, the best of these formulas is the Papadakis-Kazan, because it has 4 inputs, the inputs that are required. Because as you can see from a theoretical standpoint, all the inputs from Papadakis are there, short of M, the M, which goes into the exponents. So it's close. It's close. So there's an example in here that I urge you to go ahead and test. It's a calculator. Runoff diffusion. Okay, when we see hydrographs out there, we're going to see that they are smooth. Why are they smooth? Why are they not sharp? Why don't they have sharp edges? And the answer is because there's always diffusion in the watershed. And the diffusion attenuates the peaks. It erases the peaks, and it produces a smooth hydrograph like this. It goes without saying that if you had a hydrograph that had peaks, it means that the flow was all kinematic and subject to no diffusion. And that has happened, by the way. It does happen. In the steeper watersheds, like typically with slopes more than 1 or 2%, you will find peaks. But those are the uncommon. They're not the normal situations. Elements of a single hydrograph, these that you can review for your own over here. Components of surface runoff. Now you see surface runoff, inner flow, groundwater flow. Once you add them together, you end up with a hydrograph. If you are 3 components, these are sinusoids, but by the time they are added together and expressed in a combined fashion, it's not a sinusoid. It looks more like a gamma function. It looks more like a gamma function. And there's a formula for the gamma function, which is this one. An analytic hydrograph. I had a chance to use this in the early 80s and 90s in my projects. If I wanted to specify a nice shape with defined properties, I would use this formula. Gamma hydrograph coordinates. And flowing stream channels. Now, many of you did not have open channels, but you had hydraulics. So this is a review, flowing stream channels. So I urge you for Wednesday, review this, because we're not going to have time. You already have seen this stuff over here. And over here, in fact, I already talked about this class over here. No, I didn't talk about it in this class, but I developed a friction formula, which is 268, which is based on CIVE. I call it the dimensional CIVE. We did a lot of great things with this formula, 268. And I teach that in my open channel hydraulics class. I really am sold on this equation 258. And finally, floods, rating curves. Most people talk about rating and they talk about unique rating. But in fact, if there is diffusion, and I already told you there is diffusion, the rating is not unique, because diffusion causes the rating to become looped with what we call a hysteresis in the rating. However, in practice, most people would ignore the hysteresis, first because it's small, and second because it's hard to calculate. Now, the fact that the hysteresis is small means that there's little diffusion, and that is correct. Diffusion prevails, but there's not a whole lot of diffusion in nature. It's a very small amount of diffusion. If diffusion were to disappear, then we would have kinematic flow. But the fact is that most flows out there in nature are diffusive. They have a small, perceptible, perhaps regularly 10% would be appropriate, 10% of diffusion, not 0%. 0% would be kinematic. So with that, I'm going to finish in here. Streamflow variability, I'm not going to cover. So I want you to review, because you guys are a little bit lacking in the background. Review the end of this chapter, okay? Daily flow analysis is not too important. Flow duration either, and finally, and when I come back, because I ran out of time now, when I come back, the first thing I'm going to cover is geographical variability of streamflow. That is very important. So let me stop there. Thank you. Any questions? Okay, well, I'll see you Wednesday. I will cover the last part, the last section of this, of what we didn't do today. We ran out of time. And then I will get into the overland flow, the mathematics of overland flow. Hold on to your seats, because that's a tough subject.